Welcome everybody, my name is Ricardo Vinuesa. I'm an associate professor at KTH in Stockholm, and today we're going to conclude this first series of ML methods started with SVD, with the singular value decomposition, by talking about the widely used proper orthogonal decomposition. So this is a method that is very popular in fluid mechanics. There's other applications where this is used. As we mentioned in the previous videos, the SVD is at the heart of the POD, but is also very closely connected with other methods such as the PCA, the principal component analysis. So in today's video, we're going to be focusing on how the POD can be applied, can be calculated and interpreted in the context of fluid mechanics. So without further delay, let's dive into it. We're going to start with the proper orthogonal decomposition. So this is commonly known as POD. Okay. Basically, this method was introduced in the context of turbulent flows. In the context of turbulent flows, by Lamley, and this is in 1970. Okay. Now let me talk a little bit about POD compared with other decomposition methods. In future series, we will talk about other approaches, for example, the dynamic mode decomposition, DMD, using autoencoders and different varieties of autoencoders to produce reduced order models. Let me just focus today on the POD. It has several advantages, so let's start talking about the pros of this method. So pros. It exhibits fast convergence. It's also good in terms of reconstruction, so we can obtain good reconstruction with relatively low amounts of data. And here I want to highlight what we mean with relatively low. POD is a linear method. So essentially, we are having, and you can see that also from the SVD, we're having an optimal reconstruction from a linear point of view. So with a relatively low number of modes, and this would be the left singular vectors that we were talking about in the context of SVD, with a relatively low number of modes, we can get a good reconstruction of the full signal, of the energy in the context of turbulence, the turbulent kinetic energy of the flow. Again, we will elaborate more on this in future series, but for now, we will stick to this comment of relatively low number of modes. This is in fact connected with the property of optimality. And there is another very important and helpful property of POD, which is the orthogonality. So what do these two properties mean? From the perspective of the optimality, what we have as the first property over here, in the perspective of the optimality, we have, in a linear sense, the best possible reconstruction of the original signal. And that's everything that we have been talking about from SVD. We apply the matrix decomposition. If we retain an adequate number of modes, we can still keep the equal sign. And when we start to have an R, remember this R variable, which is the number of modes that you are keeping, the number of columns in the left singular, the left singular vectors in the U matrix, the number of columns of the U matrix. For any R that you keep, for any number of modes that you retain, POD is the optimal linear reconstruction. Now, autoencoders, and we will talk about them. We have also several videos in the channel about them. They allow us to use nonlinearities. So we have a set of nonlinear latent, we have the latent vectors, and we apply a set of nonlinear operations in the decoding operation to try to reconstruct the flow field from a smaller number of instances of representations. But in a linear sense, POD is optimal. You cannot beat the amount of reconstruction for a given number of modes R. On the other hand, we have what is called the orthogonality. These modes are orthogonal, which means that if we project them in space and in time, what we obtain is actually no overlap between those modes. And that's important. That's important because this really allows us to make quite effective predictions and quite effective interpretability when looking at those modes. Okay, so these are the pros. Let's look at the cons of POD. When it comes to the cons, it's not always easy to interpret certain things, and I will get back to that. In particular, when we have turbulence. Because these modes exhibit a mix of frequencies. So what happens is the following. In each of these POD modes, which are sorted by energy, these singular values are really putting ahead in the list those modes that contain most energy, each of those modes contains a wide range of frequencies. And of course, when you're looking at turbulent flows, which are quite characteristically multi-scale in space and time, sometimes it's difficult to associate those POD modes with certain elements, with certain physical phenomena happening on the flow. Of course, when I talked about before of interpretability due to their orthogonality, that means that the system is more disentangled, which means that you have separate physical phenomena on each of those modes. But when we apply that to turbulence and you have a range of scales, that's not always very straightforward in terms of interpretation. So there's some pros and some cons. And at the end of the day, this is a very widely used method because it gives us quite some insight and it has some nice advantages from the implementation point of view. So let's look at some of these things in more detail. First of all, in POD, you're sorting the modes by energy. Okay, that means that if I want to truncate and I start truncating from the right, so that means that you are starting to take modes of less and less energy, I will retain the ones with highest energy, which will be in fact the ones with the highest contribution to the reconstruction. They're orthogonal, which is also interesting from the properties of the, if we want to predict the temporal evolution of those modes with some data-driven method, having orthogonal modes will be easier than having completely overlapping modes in that temporal information. Now, DMD, dynamic mode decomposition, which we will be talking about in future episodes of the series. What happens with these modes is that these are associated to different frequencies. Okay, so each mode is connected with a particular frequency. It's easier to interpret that mode. However, DMD is not the optimal mode or the optimal manner to reconstruct the flow in a linear sense, right? Because POD is simply better designed for that. So the advantage of POD is that with fewer modes, you reconstruct more energy. The advantage of DMD is that even if you end up with a bigger model, because you will need more modes to reconstruct the same amount of energy, each of those modes is associated with one frequency, which has some advantages when interpreting results. Okay, so keep an eye on the future DMD applications. Today we're going to be focusing on POD. Now, let's start a bit to explain in practice how this is done. Let's imagine that we have M, so Madrid snapshots, given Madrid snapshots. And these snapshots are going to be X living in the real domain for dimension N. We define the inner product. As follows. We're going to have one snapshot xi multiplied by another snapshot xj. And this is triangular brackets indicate that we're going to calculate an inner product under a certain mass matrix M. I'll tell you more about it in just a second. This is how you're defining basically this inner product. Then what we're going to do is have xy xi transpose times this mass matrix times xj. Okay, so this is how we can define that inner product. Of course, what we know is that the norm of xj under matrix M, the norm square, is going to be equal to xi xj M. Okay, and by the way, sorry, I made a little typo. That should be xj. So Of course, because the modes are orthogonal, there is some properties that can be important here. If we want to calculate the norm square of the particular definition of this inner product, then you have it with xj times xj. Now, having defined the inner product, we need to talk about M, about this mass matrix. Okay, so M is a diagonal matrix containing the weights for non-uniform meshes. Important. Why is this important? Well, so far we have assumed that we have quite nice and clean data where our snapshots are expressed in meshes that are uniform in the y and x direction, even the z direction, and the spacing in time was also uniform. But in practice, when you are having let's think of an experiment or let's think of a simulation, if you design your computational mesh to try to resolve the gradients and you're thinking of a wall-bounded flow, the sharpest gradients are going to happen at the wall, right? Which means that you need to have a finer resolution close to the wall, and that resolution will get coarser as you move away from the wall because the scales are larger there. So not all the points will have the same weight, and we need to be able to account for the volume of those points when performing our implementation of the POD. Now, when you're performing a simulation, sometimes you run with a constant time step, but some other times you want to fix the Courant number such that you can adapt the time step to maintain a constant Courant number. And in that case, your sampling of the data may be not uniform. You might not have the snapshots at the same frequency in time. In that case, you also want to take this into account and, in a way, reproduce the non-uniformity in time so that we can properly account for the temporal interval associated with each of the snapshots. Okay, so the mass matrix M is going to contain some of the information for non-uniform distributions of the data. So in this case, we're going to focus on the mesh. We're going to talk later about the non-uniform spacing in time. If we talk about the mesh, about the non-uniform distribution in space, in general, we're going to do the following. For simplicity, many examples are with uniform meshes, okay? But we should not forget that a non-uniform mesh distribution requires a different type of analysis through the mass matrix M. Now, what are we doing with POD? Let's try to look a bit more into details. In a nutshell, what we want to do is express the spatiotemporal signal, which could be the velocity or the velocity vector. Right? So the velocity depends on space and time. We want to express it as a sum of functions where some of them depend only on space and some of them depend only on time. So we have these spatial distributions which are fixed, and they are basically they're scaled up and down by those temporal coefficients that are associated with those spatial modes. Okay, so with POD, we find deterministic and orthogonal basis and these bases are basis functions, which we're going to call capital phi. Okay, these functions are they can be vectorial functions, right? Because they will have components in u, v, and w if the flow is 3D. So these are deterministic functions, and their time coefficients and these time coefficients are going to be contained in a matrix A to decompose the snapshot matrix X. Okay, The snapshot matrix is basically the data matrix that we have been talking about, which contains in its columns all the snapshots, the Madrid number of snapshots with Norway resolution in space. So basically what we want to do is to write our snapshot matrix X as a function of these spatial functions and these coefficients in time. This can be further expanded as follows. Phi times capital sigma times V transpose. Okay, this is very important. And of course, this must look very familiar, right? This is basically the SVD. We have just changed slightly the notation where, this phi, these are the spatial functions that used to be the matrix U, which contains the left singular vectors. Then what we have is this matrix sigma, which is the matrix containing the singular values. Those are basically measuring the scaling up and down of the coefficients. And matrix Vt, which, remember, it contains the right singular vectors. That matrix is actually going to be associated with the temporal coefficients. So the product of those temporal coefficients, in particular, V contains the temporal evolution, so the frequency content. That's going to be scaled up or down by sigma, by the singular values. Those two together will make up the full temporal coefficients that are regulating our spatial functions, our POD modes, basically. Good. Important notes. Let's get into it. So a couple of important notes. The norm of matrix phi under the mass matrix M is the identity matrix Norway times Norway. And the norm of the matrix containing the temporal coefficients under a matrix N, and I'm going to tell you more in just a second, is the identity matrix Madrid times Madrid. Okay, so what does this mean? If we look at the matrix phi containing the spatial modes, so this one, what we have is that the mass matrix M is going to account for non-uniformly spaced points in space, right? So the mass distribution is going to look at measures that are not uniform, and therefore, if we use that to weigh the modes need to have a norm of 1 at the end, right? That's very important. The modes need to be normalized, and we're going to be using the inner product that I talked about before in such a way that we can add up the norm to 1. We're going to use a different weighting matrix, which we're going to call N, so capital Norway. That matrix is going to account for the non-uniformity in time, because the data is not taken at a constant time step. We can account for the variable delta t in this matrix N, and that will give me another identity matrix, in this case of size Madrid times Madrid. Okay, so that matrix N, let me just define it. N is a matrix of size Madrid times Madrid, okay, and it's a temporal weight matrix. Temporal weight matrix, which is for non-uniform delta t, and this should be an N. Okay, so for non-uniform delta t, I'm going to be using this N matrix to basically take into account that delta t is variable. Okay, so far, the only thing we have done is apply the SVD. We're trying to give a bit of an interpretation to these matrices, and we're accounting for the fact that both in space and time we might have non-uniform distributions, but at the end of the day, we have just done an SVD. Now, we're going to call this equation star. Okay, star is going to be the POD, the preproportional decomposition. But to obtain star, we need to take into account the mass matrices that we're going to be using for the non-uniform distributions. So to obtain equation star, okay, we compute the following SVD. Matrix M raised to the power of 1/2 times matrix X times matrix N raised to the power of 1/2. So capital Madrid times x times capital Norway. Okay, and this will give me basically different versions of these matrices. So I will have phi hat times sigma times v sorry about that, hat transpose. Okay, so we basically compute the SVD not on the original matrix X directly, but we're going to use the weighting matrices in space and time first. That will give us a slightly different matrices phi and v. Now, notes. Phi hat transpose times phi hat is equal to the identity matrix Norway times Norway, and v hat transpose times v hat is the identity matrix Madrid times Madrid. This means that both matrices are actually unitary, as we have been talking about over the last videos. These are unitary matrices. Remember, matrix phi is connected with the matrix U of the SVD, the left singular vectors. Matrix V here is basically matrix V from the SVD containing the right singular vectors of our decomposition. We're getting there. Now that we have computed the SVD on this scaled matrix, we can calculate the POD modes as follows. The POD modes are obtained as and we do phi times m to the minus 1/2 is going to be equal to phi hat. So I can just take the phi hat that we know and undo the scaling that we did with the mass matrix. So in a way, we're just applying the SVD on the data matrix, scaling with a non-uniform space and a non-uniform time to go back to the proper phi matrix, the proper POD modes. What you do is undo the scaling, and then you're already there. The temporal coefficients, on the other hand, let's go to the next page. The temporal coefficients can be obtained as so we have V is equal to n to the minus 1/2 times V hat, which means that using equation star, remember that equation star was in the previous page, so this is equation star that we're going to use. Remember that here V is connected with matrix A and matrix sigma. Okay, so using the relation in equation star, we can go back over here, and using star, what I have is that matrix A is basically the product of sigma times V transpose. Okay, so once again, I applied the SVD on the data matrix scale with the M and N matrices. Now I undo the change, now in the case of time, so I basically apply the N raised to the power of minus 1/2 to go back to V without the hat, and then multiplying by singular values, I recover the A matrix, which contains the temporal coefficients. Therefore, the POD expansion looks as follows. The POD expansion will be U as a function of x and time, and U is the velocity vector, x is the spatial coordinate, and t is time. So the velocity components are going to be equal to a mean flow, okay, which will be basically the zero mode of the POD expansion, and that depends on x, plus the sum from I equals 1 to m minus 1, Madrid minus 1, of ai of t times phi I of x. And this is a vector, and this is a vector. So this is the POD expansion. Let me go in more detail to each of the things in this equation. Now, U is the velocity vector, which usually has 2 or 3 components, u, v, and w. We have the mean flow, which will be the zero mode, and the expansion here is the product of the spatial modes and the temporal coefficients. So if we want to now go a bit more into details, this would be the 3 velocity components. This would be 3 spatial coordinates. This would be time. Now u0, that would be the mean flow. And the mean flow actually shows up as the zero mode. So the mean flow, zero mode. This over here would be the expansion that we're going to do. And here we have the temporal coefficients. And this over here would be the spatial modes or the POD modes. Okay, so up to this point, now we have the POD. Now we know how to use it and how to calculate it. If you're interested in additional feedback, reach out to me. We can share some codes and some implementations, but of course, I recommend that you implement it yourself. It's quite straightforward. And the main thing of this method is that you can really try to get some insight into a number of flow configurations. So very happy to have completed this series, introducing the SVD and concluding with the POD. Please reach out if you have any questions. And as always, we're always happy and delighted to collaborate and to discuss more. And feel free to come for more videos in the future. Have a good day.